will be ready shortly. So welcome everyone. My name is Lars Benson. I'm the CEO and owner of CSA Z259. We have had 4 seminars now in these COVID days. Our aim here at CSA Z259 is, of course, to connect all the stakeholders in the wind industry in North America and, of course, in Europe as well. And what we do is basically introducing new technology from Europe to North America and vice versa. Based on that, the industry is more mature, so to speak. In Europe, of course, most new technology is coming from Europe to North America. Before I introduce our moderator, I just want a little bit about the technical stuff. I can see there's a chat on the right side, and just to see if it works for everybody, can we get a high five from everybody just to see if it works? Boom. It's coming in, it's working. Perfect. Thank you, everyone. During the seminar here, there will be also polls coming up that you can answer once they come available. We cannot see or hear any of attendees. So you can put your hands up and feel free to ask any questions you want. The moderator will, and also in the background, we will try to catch all the questions as we can, and we will forward them to the presenter. So the format is 90 minutes, and we will keep us to the 90 minutes. I know people have different stuff to do afterwards, and it will be the 3 presentations about. I'll let Chris do the introduction of every speaker. Chris is in the health and safety and probably one of the most experienced health and safety specialists in North America. He will also be a moderator, so I will leave it to Chris kind of start off these sessions, and then he'll also wrap it around at the end of the presentations and also be moderating the Q&A session. So we expect that the presentation will be done in less than an hour, and then we will have the Q&A afterwards where Chris will be the moderator. I'll leave it over to you, Chris.
Excellent. Thank you, Lars. Everybody is able to hear, but yeah, so I have a brief little presentation that I'll go over first, and then we'll kind of go through the sequential order of the floating heads that you see on the screen there. And I believe, Jacob, you were going to start a poll for me at some point. Is that correct? Or can I bring that up, maybe? Okay.
Yes.
Okay, so I'll start with my slides. I'm assuming everyone is able to see that for now. So without understanding, I mean, we've got quite a few people here, and without understanding the safety backgrounds of everyone who's here today, I'm going to try and keep this fairly high level. There's definitely a time to get in the weeds and look for the nitty-gritty details, but particularly with safety, if you're trying to paint with a broad brushstroke, sometimes a simpler approach is better. Sometimes low-tech is high-tech at some point. I know that the Global Wind Organization and many of the OEMs out there will offer basic safety training to their field technicians. I don't have 2 weeks of your guys' time today, so I'm going to really compress that down, and we're going to call this very basic safety, mostly due to the time we have here. So there's not going to be anything new or revolutionary. These are all fairly old concepts, but I think they still hold value throughout the years. And I guess I'll let you be the judge of that as we get a little further forward. So just one more time, I'm going to see if we can get the poll started. Lars or Jacob, do you guys have that available? Okay. There was one of my slides, there we go, later on. So I was going to have a sort of a rhetorical, theoretical discussion about polling the audience, but through the miracles of technology, we are able to do that in real time. So if you were, your company and say your closest competitor were the final 2 finalists for, the contract of a lifetime, right? And your price was the same, your timelines were the same, everything was the same. The only thing that was going to make the difference and get you that bid was going to be your, your safety performance. So what would what would you initially think of when you're thinking of safety performance, and what would you try and highlight within your company? So we'll leave that live for a little while here, and a couple slides later, we'll kind of check back up on the results and see where we are. I'm already pleasantly surprised at what I'm seeing. I thought it would be somewhat different, but anyway, we'll move along here. So if I can get to my next slide. So to start things off, we're actually going to go back in time, almost 100 years, and look at some of the early accident models that came to be. And even the term accident is fallen out of favor somewhat in the safety community, since it implies that there was nothing that could have been done to prevent it. Today, we'd prefer the term incident. And one of the first ones to come up was a guy named Herbert Heinrich. He worked for an insurance company. Insurance companies are not in the business of losing money, so they found a lot of value in having him go through thousands and thousands and thousands of records of car accidents. And through his research, it was actually published, and the triangle you see to the right there, I know it doesn't look like much for all that work, but that's known as Heinrich's pyramid, is what it's known as today. What he found from his research was that for every time there was a major incident, so a fatality or otherwise debilitating event, injury, during that time there's also often 29 minor injuries, so broken toe, cracked ribs, cuts, scrapes, bruises, those types of things. And then there was also about 300 what he would call near misses. Now these aren't what we would think of today as a near miss. These were still car accidents, just that there was no injuries that took place. So if you and your organization plan to have between 250 to 260 car accidents before you start looking, with no injuries, before you start looking at putting some prevention steps in place, please give me a call after this meeting here. I'd be happy to take a lot of your money over the years and try and drag you kicking and screaming to the 21st century. But hopefully I can convince you otherwise over the next few slides here, since that's just not the way we want to do things. A couple of years later, the same guy, Heinrich, came up with what he called the domino theory of accident causation. And what that referred to was, if you had a set of dominoes lined up, and each one of those dominoes represented a sequential step or an event or a condition, and you were to, knock those dominoes over, the last one being some sort of harm that would happen, there's nothing that can happen once those are set in motion. What Heinrich theorized was, you take any one of these conditions, they all represent something different. If you take any one of them out of the array, it doesn't even matter which one, that final domino never falls. The harm never occurs. So that was, some of the first inklings of thinking about prevention that went into some of the safety modeling. Then if we fast forward about 40 years, a guy named Frank Bird, who was also in insurance, he went through, I think it was just over 1.7 million records of car accidents. And he expanded on Heinrich's pyramid somewhat. Instead of the 1 to 29 to 300 ratio, he came up with an idea that was 1 to 10 to 30 to 600. So 1 again was the major injury, 10 was a minor injury, 30 referred to property damage incidents, and then 600 was near misses. And those would equate a little bit more with what we would think of as a near miss today. Then if we fast forward again into a time that hopefully most of us can remember, James Reason in his book Human Error in the early 90s gave us the Swiss cheese model. So we're thinking about prevention at this point. We're putting some levels of protection in place or some barriers. Now none of these barriers on their own are completely impervious. So they do have their weaknesses, sort of like holes in Swiss cheese. And every now and then the stars would align just right and the holes in the Swiss cheese would line up and that harm would be able to find its way through and have its effect on you. So if we're thinking about prevention, we could put extra barriers in place. We could think about what the hazard specifically is. We could try and tailor our prevention efforts towards that particular hazard, make the holes a little bit smaller, make it a little less likely for them to ever line up. And that's kind of how that one went. So using any or all of these models, we can't really predict the future to the point of buying lottery tickets, but we can definitely have a pretty educated guess on what may happen. Now, when we're starting to guess with people's lives at stake, we probably want to have the most accurate data set possible. So some of the factors that could go into that, there's quite a few different ones, and I guess that's what the poll here kind of refers to. So I'm quite impressed that we did get almost half the people were going for the one that I was thinking of. So on the next slide, I'm going to focus to begin on the right side of the slide, since that was where my suspicion sort of lied that see some last-minute answers popping in there. Most people would probably pick the recordable rate. Now, there's nothing, nothing wrong with that. That rate isn't without merit entirely. It's reasonably well defined. It does a decent job of comparing apples to apples across, a wide variety of industries and organizations. The problem with the recordable rate is those people have already been injured. You can't go and uninjure them after the fact. And that's the same for all of these lagging indicators. You're waiting for something bad to happen till you take the information and do something with it. So there's got to be a better way, right? There's, we could look at try and find out what could happen. And that's where the leading indicators come in. Those are things that haven't happened yet, but they're giving you some information on what might happen. So one we might want to look at would be the hazards that are reported. Now, just reporting them isn't enough. I mean, hey, we had 1,000 hazards reported last year. Great. What were they? Oh, I don't know. Okay, so those numbers by themselves aren't worth anything really. It's what those numbers represent that have the real value. So subcategorization. Now you can slice and dice these dozens of different ways. 100 different categories if you like. Again, keeping things high level, I'm going to suggest 3. So environmental, property or equipment damage, or injury. Do they relate to any one of those 3 things? Whichever one of those buckets gets filled with the most hazards, that's where you direct your prevention efforts. Now within those categories, you can subcategorize again and slice and dice again, find out where the greatest hazard lies. That's where you direct your prevention efforts. And then hazards corrected is another one. So last week, let's say you had 10 hazards reported. 7 of them referred to patch of ice outside the office door, and 3 of them were bunch of stuff piled in front of an emergency exit. So do you actually have 10 hazards, or do you have 2 hazards, right? If you're seeing the same hazards come up over and over and over again, your prevention efforts aren't effective enough, right? It's time to try either more of them or something different, or keep trying until you get something that works. Inspections is another great one. We're going out and actively looking for hazards, before they happen. Look for the unsafe conditions that are out there. And these can be highly technical, multi-page documented formal inspections, or they can be as informal as walking around your truck before you drive away. Just look for, hazards, that type of thing. It can be really simple. Pre-work safety briefings, these are another easy one to keep your finger on the pulse of what's going on out there. These are not a sign-in document to prove you're there to get paid. These are to talk about what are the hazards that is unique to this job compared to other jobs. And even more importantly, within that same job, what's different about today that I need to be aware of? Is there high winds coming? Is there ice on the blades? Is there a new guy in the crew? Did somebody's cat die last night? Whatever it is, right? What's different about today that we need to be aware of? So despite all our best efforts, sometimes things still go wrong, and that's okay. When the Space Shuttle Challenger explodes, when the Titanic sinks, those are major incidents, right? There's no expense spared in the investigation efforts and the follow-up that comes with that. And that's valid. Those are pretty big deals. They deserve some attention. But how often does a spaceship explode? How often does a Titanic sink? These just don't happen every day. So there's not as much there as there is with, say, 7 times last week there was ice outside the office door. What caused that, right? Do we need to fly in a team of international experts to investigate that? Not likely, right? That could be solved, a lot easier for a lot less expense. It never hits the newspapers, those types of things, right? Chances are, it probably doesn't get investigated. I'm pretty good on ice. Most of you probably are as well. I could probably get in that building. I'm good. So you get in there and you're fine. But 99 other people work in that building. So, you got 100 people, 99 more need to walk across that same ice. And you know what? Most of them will probably make it. Let's say maybe 20 of them slip. And of that 20, they don't all even fall down. Maybe 4 or 5 fall down. And of that, only 1 maybe bangs their knee. So not a bad day, not a big deal, right? We're not talking Challenger or Titanic, level of disasters here. So next day, same thing, 100 people show up, either the same 20 or a different 20 or whatever mix you want, slip. Maybe 4 or 5 fall, and somebody bangs their elbow. How many times do we do this before somebody lands on their head? How many times do we do this before somebody breaks their neck? Right now, you have an investigation coming. Now you have regulators coming. Now your recordable rate is shot. Now you're getting a lot more attention on it, right? And it maybe didn't even need to be that bad. So, some of the things we could look at for prevention. Here's another triangle. Safety guys love triangles, by the way. So, best case scenario, the gold standard is elimination. So let's move that office to Florida. We're not going to have a problem with ice outside the door anymore. Now, that's not always easily achievable. It's the most effective, but it's a lot more difficult to implement. What I see quite often is on the other end of things is PPE. That comes up on almost every incident report I've ever reviewed. better hard hat, different glasses, different PPE of whatever type. And that's not without merit either. I mean, there's a time and a place for that, but it should not be your go-to every time, right? We definitely need to have PPE, and hopefully I'm not the first person to tell you this, but PPE is your last line of defense. In my opinion, too many other things have gone wrong if your PPE ever has an opportunity to save you. So there could be other options, right? There's different levels within here, and we want to mix and match, much like the Swiss cheese, put a whole bunch of them in place. Administrative controls. First person to show up from October to April. There's a bucket of salt inside the door, spread some salt on the sidewalk, done. Now you're only putting one person at risk. Engineering controls. Maybe you spend some money, put in a heated sidewalk, melts the ice. Substitution, maybe use the side door or the back door where there's not as much ice. Or, elimination, hey, let's all move to Florida. So those, again, try and mix and match, find the balance of the most effective ones. Your leading and lagging indicators will, give you a clue as to whether you've been effective or not. So that's essentially the end of the very basic safety lesson. Within the wind industry itself, we do have unique challenges, absolutely. Just the nature of the construction of a tower. I mean, most of the work takes place 300 feet in the air. So there are unique challenges to our industry, but these concepts we've talked about, are still entirely applicable. They've been so for the last 100 years and will likely continue to be. So my challenge to you, today, with the next presenters and then just in your everyday work, is to look for elements of where you can see these concepts at play, right? So you look for these in your regular work, and then for the other presenters today, try and find, are they collecting data? Are they analyzing the data? Are they taking action based on what they're seeing? Are we looking at leading indicators versus lagging indicators? Are we looking to eliminate hazards? Those types of things, right? I think you'll be surprised once you start to look for them. You'll probably see them everywhere. So I think we'll probably save questions for the end, if I'm not mistaken. But
Correct. There'll be a Q&A afterwards. I think we have to jump to the next presenter to keep our, to keep our timeline here.
Absolutely. Okay, so the next one up will be Christian Bach. Christian has carried out research at the Technical University of Denmark since 1997 and is now head of the new Poul la Cour Tunnel, where his focus is theoretical and experimental airfoil and rotor aerodynamics and aeroacoustics. He's co-inventor of active trailing edge flaps, and he's a handsome gentleman on your screen right now. It's all yours.
Yeah, thank you. I'll just get my presentation in play like that. Right. So here you can see the title, Eroded Leading Edge Impact on Performance and Noise. And I want to present some of the work that we have done at DTU Wind Energy. I'm from DTU Wind Energy. It's based in Denmark, and we are a department of 250 persons. We have an experience of over 40 years with wind energy, and we are working within aerodynamics, for instance, aeroelasticity, meteorology, composites, and structures, and almost everything within wind energy. But for now, it's aerodynamics, and I will just talk about what we have done, some of the things that we have done. So maybe a bit rhetoric question here. Are damages affecting the aerodynamics, and how does it look like? I guess that it will actually do something to the aerodynamics. So some of the wind turbine owners experience is a power curve like this. So here we can see the power as a function of wind speed, and the red curve shows as the power curve is the first year, and then the next year it is the blue one, and then the third year is the green one. You can see how the power degrades over time, and the annual unit production drops from 100% the first year, 97% this second year, 96% the third year, and so on. So something is happening here, and it could be many things, but it is likely aerodynamics that is actually causing this. So this is, for instance, photos of a blade, or actually 3 different blades. So here you can see it's blades that has been inspected. Here is you you can say sandpaper-like types of damages where you have eroded the very leading edge, and this is probably just raindrops that has eroded this. So these raindrops are actually turning into kind of stone when the blade runs with 90 meters per second. That is, it's fast, and it's much faster than cars and so on, because we are up at 300 kilometers an hour. Or 100, what is this? It's 200 miles per hour or so. That's a lot. And this is another kind of damage, this void at the leading edge. And then we have other damages like voids downstream of the leading edge. So this is some of the things that you can see from real life. And we have, of course, investigated this, and it is a bit difficult to investigate because there are so many different damages on wind turbine blades. There are more damages on wind turbine blades than there are blades, because probably there are more than one damage per blade. So we just have to find a way to do this, just to investigate what will degraded blades do to the aerodynamics. We have used this fairly new inaugurated wind tunnel at the DTU, the Poul la Cour Tunnel, inaugurated in 2018, and is dedicated for wind energy. So we are able to run at fairly high flow speeds, fairly high models or big models, and then we are also able to measure acoustics. So that's important in wind energy, and is also it's rarely done in wind tunnels that you can actually measure noise. So this is this combination that is very nice with this tunnel. And this is a photo from the test section, so you can see we have the wind in our back, and then we look through the test section, and we can see a vertically based airfoil in a test section that is 3 meters wide and 2 meters high. And this airfoil is then based in or mounted in a pitch bearing or turntable, so we can rotate this airfoil and find out what will the forces be on this airfoil. And it's important to know the forces, because this is what creates both the forces on the construction, on the wind turbine, but also the power, the forces that actually drives the blades. So this is can be quantified in the test section here. And then we have another configuration of the tunnel. So you can see, if I just back, you can see these hard walls where you have windows in the walls, and then we have the Kevlar walls. Now you can see it on the left photo from the outside, where you can see the Kevlar wall and then a microphone array with 84 microphones. And on the right picture, you can see a photo where this Kevlar, the yellow wall, has been removed, and now we are actually just testing the sound. So this is then the test section in this anechoic room, where we have these special walls that absorbs the noise. So how do we test damages? Well, this is just one example of how we can test these damages. This is kind of a sandpaper. There's the rough one to the left and the more fine one to the right. And this is simply just to test how the different textures of topology of the leading edge will affect the aerodynamics. So this is simply just two examples, and we have tested a lot of different other surfaces just to test what is happening to the aerodynamics. So here is then some of the results from the wind tunnel. You can see this is in the mid plot, you have a lift as a function of angle of attack, and then to the left you have lift as a function of drag, and to the right you have lift as a function of lift over drag. And what you can see is that maximum lift from the purple one has dropped. That's the clean case. But if you use this sandpaper type, then it drops, this maximum lift drops to another level from lift coefficient of 1.4. Then it drops to 1.2. And that is almost 20%, 15 to 20% drop in maximum lift. That is actually also going into the forces on the turbine, but also the power. So not only is maximum lift or lift as such dropping, but also drag is going up. You can see this to the left. So drag is increasing from the purple one, that is the clean case, up to the rough case. And that's a significant increase in drag. And to the right, you can see lift over drag, where you have, again, the clean one is the purple, and then you have, it drops from 110 to 50. So it's more than halving the performance. So that's a lot. You can actually drop the performance by having something at the leading edge. And noise is actually very new, so it's not more than some weeks ago we tested this, and I haven't heard about this before, that noise has been tested on some leading edge performance, leading edge damages. But here you can see that in the clean case we have a certain noise level, but with a mesh we actually have a reduced noise level, at least at the higher frequencies. And that's interesting. And then, and this was then at 5 degrees angle of attack. And if you go to 8 degrees, you have the same tendency that you have a decreased noise emission. But noise is kind of tricky. So we have to investigate this further to find out what is this actually doing to the rotor noise, because this is just on an airfoil. What's happening if we have this situation on a rotor? So that's important to find out about this. But this is very new, and I will call it preliminary results because it is very new and we have to look into this further. Okay, we have investigated this with computational fluid dynamics, and we've also investigated airfoils. So to the left, you can see different kinds of airfoil topologies. This is the leading edge where we have a void into the airfoil with the orange color, and then a bump out, that is the blue, maybe representing leading edge protection. And then you can see different types of lift coefficients or different, you can see different lift coefficients predicted with computational fluid dynamics. So lift as a function of angle of attack to the right, and lift as a function of drag to the left. And here you can again see that drag is increasing with different types of erosion and bumps. And you can also see that maximum lift can drop a lot with the leading edge roughness at the very leading edge. And if you use this knowledge, for instance, from the computational fluid dynamics, you can take some of these data, put into the performance of a rotor, and see what's happening. If we, for instance, to the left, can see this power curve, then we have different wind distributions. So we have the low flow speed, that is the brown curve. Then we have the 7 meters per second, that is the blue one. And then you actually have more and more wind or energy towards the high wind speeds. So that's, you can say, the Weibull distribution, that you can change this to investigate what this means to the energy production. And to the right, you can see what is happening if I change my maximum tip speed. So this is happening also in for the higher flow speeds, that you change this maximum tip speed. So this is a study where we investigate the tip speed influence, and also the Weibull distribution, you can say the climate. And if we then take a look at the rotor, we investigate the outer 30% of the blades. We have the outer 30%, then we have the outer 20%, and the outer 10% covered with these damages. And you can see to the right power as a function of wind speed, where you can see how the power curve is influenced by the tip speed. That is actually, the lower the tip speed is, the more it is actually, the lower the slope is. But you can also see with the dotted curves that the dotted curves should be compared to the solid curves. And you can see how much is lost if you have leading edge damages on an airfoil on the blade. So this is kind of to sum everything up here in this study that we made. So the top row shows what's happening at 6 meters per second in average wind speed. The middle one is 8 meters per second in average wind speed, and the bottom is 10 meters per second in average wind speed. And then the left column is the outer 30% covered with damages. Then the mid one is the outer 20% covered with damages, and the outer 10% covered with the damages to the right. And you can see how the losses, so you can see these plots shows AP loss as a function of tip speed. So each of these plots can then reveal that if you have high average wind speeds and not so much damage on the blades, the outer 10%, then there is below 0.5% loss in energy production. But if you have up to low average wind speeds, 6 meters per second, and 30% covered with damages, then you can experience maybe up to 3 or maybe 4% AP loss. So there's a huge difference in what you can experience in losses depending on the site, how much wind you will have on the side, and how much the blade has been damaged. So this about talking about how the eroded leading edges will actually influence the performance is very dependent on the turbine and the site, and this is what this is illustrating. I have to move on to the conclusion. So a roughness corresponding to a mesh, as we just saw in the slides before, result in a significant reduction in airfoil performance. But it also results in a change in noise emission. And I won't say it is a reduction of noise emission, even though we could see it from the plots, but it depends on, you can say, also directivity and so on from the noise. So you really have to investigate this noise map very carefully to take the right conclusions. But at least we can see changes in the noise emission. And apparently the trailing edge noise will reduce the noise if there is roughness, but we just have to investigate this. AP losses depends slightly on tip speed. AP losses also depend significantly on the extent of erosion over the blade and also the wind climate. And then we can see AP losses, at least in this investigation, of up to 4%. And we could also see, and that was not, I really hadn't had the time because there's so much to say here, but we could see that AP losses were significant with this bump type that actually corresponds to a leading edge protection. If it is only the first 3%, that is actually causing some AP losses. So it's also important to be aware of these bumps over the leading edge. So this was what I wanted to say. Thank you. And I guess that questions can be answered just after the other presentations.
Yeah, absolutely. If you folks have questions along the way, throw them into the chat there, or we'll definitely collect them all at the end, and we'll have plenty of time, hopefully. Next up, we have Dr. Carsten Vestergaard, who has 25 years of global wind experience. He's a senior advisor to the Sandia National Laboratory's wind program and a lifelong inventor. He's formerly a professor of practice at Texas Tech University and global technology director at Vestas Wind Systems. And here he is now.
Thank you, Chris, and thank you, Lars, for organizing this. I will pick up where Christian sort of left off and talk about a tool that I've developed to convert some of the research that's been going on in the community, such things like we've just seen from Christian and many others that I've reviewed and put in together into a more practical tool, if you like, where instead of using information that we don't have, try to condense it down to the information we do have and then convert that into something practical. And the reason I've been focusing on this in the last couple of years is that leading edge erosion is definitely becoming a more dominant part of the blade repair budgets across the fleet, and it's a growing problem. The energy losses associated with this remains at large, unquantified. And also when we upgrade and repair, sometimes we'll see some examples of not quite getting back to what we thought we were going to do. And I'll illustrate this with the tool that I've developed and how we can quantify this more accurately. In the figure over there to the right, I have taken the 50,000 turbines, just the large ones and the ones in larger wind farms in the US fleet, and then I computed with the local rain rate what is the average erosion category per year that the fleet would experience. And as you can see, up to about 2011, it was pretty flat. And then what you've seen in the last pretty much decade, you've seen an increase in the average erosion rate that turbines fleet. The main driver of that is simply that the tip speeds that Christian were talking about are increasing, and that causes that additional erosion rate. And I also computed with the tools that I've developed the average loss of the entire fleet, and it's about 1.3% of the loss. But what's maybe more important is that it escalates about 0.3% per year. And so I'll get back to that and show some examples on that later in the presentation. And what may surprise you is that about 45% of the total loss of the 1.3% actually originates in damages from category 1 to category 3. So that may be something that you need to consider just as the basics for when do we want to repair. So like I said, the tool I've developed is a tool that's focused on leading edge erosion prediction. And the tool can predict both the damage progression and also the associated annual energy loss that comes with that loss. It's made as simple as you possibly can, so I try to condense the amount of information you need to actually do these calculations. And I've condensed it down to where you don't need proprietary data, so you don't need to understand the blade shape, you don't need to understand the airfoil shapes. You really just need some very generic information. I'll walk through that. And I also added a generic catalog of leading edge protection products that Kirsten talked about, the bump, and I'll talk a little bit more about what that means in practice and things to look out for. And what that enabled us to do is really, if we have the ability to quantify leading edge erosion, both for every turbine and every wind farm, then it really allows us to create a fleet overview, both past, present, and future status, and we can make more intelligent operational decisions, and we can look at future repair budgets. And the tool is developed really for integrating into business processes based on an Excel integration, but you can also do it in other ways. An example of using this tool, again, for the same 50,000 turbines we just talked about before, I said, well, when relative to their construction year, which year would they reach a category 3 damage, everything else even with the local rain rate and so forth. And that, you know, the graph here shows the increase that we've seen in repairs and the need for repairs. You know, of course, it tapers off. As once they repair it, they go out of the queue. But presumably, we will have new turbines coming into the queue, and this is not a challenge that will just disappear by itself. If you take a step further and integrate visual inspections into the tool, then you also get a status, and you get a starting point that takes away the things that we don't know, for example, manufacturing flaws and individual variability from blade to blade. If you do that with a digital asset management tool, such as the one from Moderator that I've been working with, then you also get a lot of consistency into your process, and then you also get a much stronger tool to do a full visualization of your entire fleet and the progress there. So we will talk a little bit more about what this tool actually is. So it starts with a power curve. Christian showed some calculations of power curves. But one thing I'd like to point out is that the differences between the different damage categories is really small. And they're really smaller than you can measure from some SCADA data and even very, very precise, long-lasting, accurate measurement campaigns. The tool is developed in Excel, and so it's a common Excel spreadsheet. So the power curve tool in itself, what you need is basic information: turbine rating, diameter, RPM. You need some default loss factors. You can tune them a little bit if you like to get the shape of the curve just right, but it's the default is pretty good. Yeah, density cut in, cut out, and then wind speed on the side or wind distribution of the side, or you can just use the default relay distribution for sort of trends. And then when it comes to the leading edge part, the way I've defined the tool, so it's a definition, it's not a scientific measure here, it's a definition. So simply just you pick the worst category damage that you have on your blade, and then you pick the length of the damage, and that's how the tool works. That's all you need. You don't really need any details about what's going on in between. And what it does, as an example there to the right, you can see the blue curve is category 2 damage, and then the orange curve is category 3 damage. And there's two effects that influence the power curve. One is a reduction in CP, so that's the middle of the curve, around 8 meters per second, if you like. And then the second part of it is that once you have that lift loss that Christian was talking about in the previous presentation, you get an additional little rounding of the curve up around the knee of the power curve. And it's roughly 50-50. It depends a little bit on the turbine and the configuration and so on. But the tool takes that into account. And one example more on the power curve level is that we see sometimes that folks are disappointed when they repair their blades. And sometimes maybe it's we get a little bit eager. So here's again an example with a category 3 damage blades. That's the orange curve. And then the blue curve is now represent a repaired curve. And the percentage numbers down there in the table to the right indicates the percentage loss relative to new. So we're around 2% loss with a category 3, and it was computed with a damage length of 5 meters, which is about roughly 15% of the rotor. And then in eagerness, well, we restored that with a leading edge protection product, and we thought we would do a really good job, so we had a little bit extra protection rather than just covering the damages. And we're ending up with a pretty disappointing result, I would think, for most people performing leading edge repairs, where there's a net loss is the same, essentially. Right? So, okay, we protected the turbine, but our loss was not really recovered, which I would think we would try to do, at least in that. The other thing we need to know is how strong is the protection that we put on, or how strong is the repair if we continue. And so luckily, a lot of products are being tested very thoroughly. The basic of the testing is according to an ASTM standard. And one needs to be aware that UV lights make a huge difference in these tests. A lot of product deteriorates with UV lights, so if they haven't been hardened with UV lights for the test, then they will last a lot longer than rain erosion test. But the tool I've developed has the ability to take a data sheet from the vendor, convert these tests into something that's practically usable on your turbine. So you can then figure out what is the strength of this. These tests normally do not include the aerodynamic impact. And as Christian talked about in the past presentation here, the shape and of that protection that we put on is important, and that gives us some additional aerodynamic losses. But before you get to that, I would encourage you to consider, whether it's tape, coating, sleeves, or whatever, to think about the application method. Because the application method is important. It can limit what we can do. Do we need to upgrade the surface before we restore it? And is there weather windows to put it in that are different? And of course, install time and cost is a very, very important element. And really important to consider is also, what are the failure mode of this particular product? And what does it mean if I have to make a future repair? Can I get it off again? Is it easy to get off? How do we repair sections off the product, and so forth? Those are really important questions before you even start thinking about all the other stuff. On the aerodynamic side of it, there's a couple of things to look out for, whether it's a coating, paint, or tape, or whatever. Waviness and ripples. Christian showed this net thing on there. You could consider that maybe it's sort of ripples in the paint. So if you do like a thick, gooey coating with some brush strokes in it, you know, you get ripples and irregularities in surface. That causes losses. The thickness. Christian had a backward facing bump right there before the little triangle there. That causes losses, and it depends on where it sits in the blade as well. And then that loss can be diminished to a certain degree, not completely, but to a certain degree if it has a nice taper off or a seal. And so often that seal is important for the durability of the installation, so water can't penetrate in under, if it's a tape or a sleeve or an even coating set. You don't want water and ice to come back in under and destroy it. So, like I said, with our analytics tool, then you can actually go back and you can look at the specific durability, you know, compared to your site and the site-specific performance. You can look at the AP loss after the repair, and you can also look at how it degrades over time. And then you can, of course, do a return on your investment calculations if you have that. So let me talk a little bit about how to create an overview, and then I'll go into a specific example as well. So what we need is basically some basic information. We need to know the wind farm, the type of turbines, how long it's been in operation. We need some basic parameters just with the power curve, the rated power, the diameter, the nominal RPM. If we don't know the gearbox stuff, we can just leave it a default. We need some site-specific information, air density, rain rate is really important, and we need the wind speed. We don't need the exact wind speed for each and every turbine. We can estimate this if we have a reference capacity factor or a reference production that we want to hold this up to. We don't need to know all the little details of this. Same goes with the energy price that we want to hold this up to. This needs to be held up to the budget of the repair, not necessarily the actual market price or something that may be more difficult to quantify. And then we need to know the initial blade conditions that we start with. So when you do that, we can create a dashboard or a fleet in here. I've chosen the six different wind farms here. To the left, you see the blue bar indicates just the age of the wind farm. And the black and the red line indicate onset of erosion versus the category 3 level. So that gives you kind of a nice snapshot, but it doesn't really tell you what to do. So the middle panel there, the blue bar here in this panel indicates the actual damage progression from category 0 to 5. And so the blue bar is the status, but maybe more important is to know what happens in a year. Because if you're planning a year ahead, what you want to know is not what the status is. You want to know what it's going to look like next year. And you can now see that if you look at the two outer ones, the two offshore wind farms there, one has progressed a little bit more, the one to the right, but the one to the left will actually have a much larger impact due to the conditions on the site and the actual performance of the turbine. So that gives a lot bigger impact. It also gives a lot bigger impact on the AP. That's the last chart over to the right, where the blue bar is the status, and the red bar is what's going to happen in a year. So now you can see you can get a little bit more nuanced on your priorities just within your fleet, just with this snapshot here on wind farm level. But we want to take this a step further. So I went back to the database of the US wind farms, and I took the most predominant turbine out there. There's about 145 of them, at least in bigger farms. And they have rain rates from 280 millimeters to over 1,200 millimeters. And the dots over in the chart there shows the age of the plants and then the computed erosion rate, or the AP loss. Actually, more precisely, it's the capacity factor over time. Relative to 100%. And so now you can see it's quite a large scatter there, and you can understand why some folks says, well, this is absolutely not a problem, or you can say this is a big problem. So you get quite a variety there. The dark line indicates the average of that 145 wind farm computed. And the light blue line, it's the regression line and the scatter data, is stemmed from a Lawrence Berkeley National Laboratory study just done a few months ago. I extracted those 145 wind farms out of that study, where they reported energy losses as actually reported into the IEA database over their lifetime, and then they wind corrected the data and computed the capacity factor development over time. So that's what the dashed line shows. So essentially, it gives you a sense of what the aging of the wind farm versus the erosion level is relative to each other. Erosion is pretty important on that. Okay, so let's take it a step further and try to make our data more accurate. And we do that by adding inspection. And then we go through our process, we model it, we estimate the gains and the losses, and then we can do a multi-year budget across the fleet. So we'll make an example here of that. I call it my 5 turbine example. So I inspect in 2018, I inspect my 5 turbines. I inspect all 3 blades. And so the chart on top to the right there shows the damage category as inspected, the average of the 3 blades. And then I use a model to progress what's going to happen in the next couple of years. And so that's what the line shows. It shows the average of those turbines. And you can see one turbine there has installed a LEP product, so it performs a little bit different than the rest of the turbines. In the bottom chart, since I have a status, that's the orange bars, that's a distribution of damages across the fleet of my 15 blades. And then I use the model to predict what does the distribution look like in the future. Right? So I simply use those lines that you have above, but use it for individual blades and then move that forward. So now with the distribution of damages, presumably I could go back to a service company and ask them what it would cost to repair a category 1, 2, 3, 4, and so forth. And then I can progress my repair budget. And when I do that, I can go back and I can compare my predicted repair budget as I go out in the out years, and I can compare that to my lost production. So now I can get to a very well quantified status by the inspection and what's going to happen in the future. And then I can actually quantify what am I going to need for a repair budget and when do I actually want to repair compared to my losses. With that, I would say if you'd like to know a little bit more about this, you can try, I put a very simple version of this on my website. You can try the calculator. And if you do, please let me know if it doesn't fit so we can figure out why it doesn't fit. It's often a very simple reason. If you're interested in a more integrated type approach, then I would suggest you go to the link there, Hover Data, and take a discussion with Hover around that. So with that, thank you.
Thank you. A bit of detail there, and we'll move on to our next presenter, possibly the main event, what you may have been waiting for. So Martin Huus-Bjerge is our next presenter. He's the CEO and co-founder of Robotics, providing rotor blade repair service. Previously, Martin helped Siemens achieve operational performance improvement of its wind turbines through business intelligence, and he is about to speak to us now.
Thank you very much, Chris. So yes, correct. I started in the wind industry in 2007 and started Robotics here in 2016. So been working with these robots now for approximately 4.5 years. So been a quite nice journey. So, but let's get started. I think we all know about leading edge erosion now. We heard from our previous presenters that this is definitely something we need to look into. I think all of you also know something about how we're working with this today. So having technicians working from ropes, from platforms, from cherry pickers, similar solutions, and putting on new LEP solutions. What we have worked with here in Robotics for the last years is to develop a robotic platform. So we can now put a robot on the blade, and then the robot will actually do the repair of your leading edge. So we now have a automatic solution available to repair leading edge. So how does it work? Well, basically you send a technician up the tower, locking the rotor, attaching 2 ropes in the nacelle, lowering to the ground. On the ground you have another technician who has prepared the robot. He will then attach the ropes to the robot, and the robot is then hoisted. Then from there, the work can be done remotely. Typically, we have a trailer on site where we can do control of multiple robots. The technicians will then be located safe on the ground, remote controlling the robot, positioning the robot where damage needs to be repaired, and then the robot will pick the various tools it carries with it and then start doing the repair job. I do have a small video from some work we did here in Denmark. Actually, I'll just share it with you here. So this is from some work we did this summer here in Denmark. So we have I have my own technicians here, and they bring the robot on site, all trained and qualified to enter the turbine, lock the rotors and stuff like that. We will set the ropes attached to the robot, as I mentioned before, and then we hoist the robot up. So, and as soon as the robot is then hoisted, it will eventually meet the blade, and then we pitch the blade, and the robot can then move down the blade and start doing the work. All this is then carried out from this trailer where we have our technicians located, and they can do the control of the robot. There's cameras and laser scanners and stuff like that, so they can monitor everything what's going on up there. And it's not like they're doing it's not a joystick-like control of the robot. So they give it a set of parameters, and then the robot would carry out the job, defining an area where something needs to be done. And then we'll clean the blade, and here we'll apply some filler material and smoothen it, make sure we get smooth edges, so we don't get these aerodynamic bump downs. We can have multiple robots running in the same wind farm, controlling from the same trailer. And when one area is done, we then move on to the next area and continue the job with the robot. And here we also have a LEP coating. So in this case, it's a wet LEP that is sprayed on, so it's a paint-like, but still an LEP solution. So this is very basic how the system is working. And now I just need to get back to the slide deck here. So yeah, so I think our next thing for me here is a small question for you guys. So I would like to know what your biggest concern is related to blade maintenance. Is it quality and how the documentation is done while the work is done? Is it health and safety? Is it the price? Is it now we talked a lot about the AP, and Christian also a little bit about noise. Is that your major concern, or is it something completely different? Then please, if it's something different, please put a comment in the chat as well, so we can see what you think about that. And I see we still have we're getting quite some responses in here. A lot of people talking about quality and prices as well. So just keep voting, and I'll carry on my presentation a little bit more here. So with the robot, one of the things we for sure can do something about is the quality and the documentation. With the robot, you get really high precision, and there's no skipping corners. When you have a robot up there, it always performs the same high quality. Also, the documentation is also is very good. You get there's nobody cheating with your documentation. You get always the documents that you need and everything according to the program of the robot. When it comes to safety, I think it goes without saying that reducing the amount of hours spent working in height is also increasing our safety a lot. So here we are basically eliminating a safety threat. We are also eliminating the amount of time where people have to work with dangerous chemicals like epoxy and paints. We related to the costs, we will definitely also be able to compete on cost with this solution. So we have less people working in the field with the robot. So one technician can control multiple robots in the future. We have an increased weather window. I'll get back into this. And then last but not least, we will actually also we have designed the platform to be very flexible, so we can actually do other maintenance tasks at the blade. So it's not just leading edge, and I'll also get back to that part. So here I just have a few examples of some validations images taken by the robot. I know it can be difficult to see all the details here, but here you have a pre-repair picture, and then we have after we have applied the coating. And if I can make your attention to the side of the pictures, there you have a lot of metadata. You can't see here exactly what it is, but this is a lot of metadata that is captured together with each image that the robot is taking during the repair process. And these metadata contains temperatures, humidities, who is the operator of the robot, what is the blade, where are we on the blade, what turbine, what robot, all this kind of information is stored together with each individual images and is automatically captured there. So you don't have photo cards where you can't read what's on the card, or someone forget to change the information on the photo card or stuff like that. So all this is automatically available when you have a robot up there. And the same, we have validation done or images taken in between each process step, so you get really a massive amount of documentation with our robot solution. So I think it's time for our next question here for you guys. I would like to know what your concerns are related to environmental limitations. So are your main concern related to wind? Is it the humidity? Is it the temperature? Is it lightning? Something different? Again, if it's something different, please put a comment in the chat. So starting to get some inputs here from you guys, and just keep on voting. But I see it's humidity and wind is definitely scoring high here. So this is some inputs on our robot. So we can work in quite high wind speeds. Currently, we've been working in 12 meters per second in 10 minutes average at the rotor height. We have gusts 15 meters per second. Then I see not a lot of you talking about lightning, but actually the robot has an advantage here. We can work even though you have lightning in close proximities. So as we don't have people up there, there's no risk of people with the lightning, so we can still keep operating while there's lightning in the area. Although I would say if we have lightning just above the tower, I would still stop the operation. Typically, we also get some rain in these cases, but you have less downtime due to lightning. And then there's the whole temperature humidity part. It's very much dependent on the LEP material used. Here, put in an example of a map from the LEP material we're planning to use here in 21, where we can work from around 0 degrees up till 45, 50 degrees, and then humidity up to something like 80, 85 relative humidity. And then we're actually also working on a solution so we can do night operations. So here during 2021, we expect to be able to start working 24/7 and have the robot working at nights as well. So in this way, we would like to help expanding the weather window of doing maintenance of blades. A little bit more about the robot and the whole system. So the core of the system is, of course, the robot itself, the blue box with the robot arm that can carry various tools. but that alone doesn't do the job. So to be able to work on site, we still need power supply, communication, we need transport equipment, we need our control center. So all this auxiliary systems need to be in place. Then there's our whole software platform. So enable us to do remote control of the robot. This is also where we're starting to build AI systems. So we will in the future have a more autonomous robot, and in this way having less resources to control additional robots. On top of this, we then have various tools that do the specific tasks. So here I have a picture of a sanding tool that can clean and sand your blade before we apply the LEP, and our squidgy blade that will smoothen the surface of the filler or LEP material. So this kind of leads me to my next question for you guys. So if we anyhow have the robot up there doing leading edge repair, what kind of other repairs or stuff would you like to have us to do when we anyhow have the robot there? So we put up some suggestions. So it could be some inspection of the blade, inspecting the structure of the blade. Do we have any structural parts that also need repair? Is it checking the lightning receptors, drain holes, doing power curve upgrades, or repairing if you have a vortex generator that fall off, place that back on the blade again, or again something else? Please put a comment. And yeah, getting some answers here. Interesting. We actually have a project coming up where we plan to work on NDT inspection. So I'm happy to see that more of you are interested in that as well. But as I mentioned, it's a platform. So with a different tool on the robot and a little bit of upgrade to the software, we would actually be able to do other things on the blades when we anyhow there. So we would like to do testing of lightning receptors, maintenance of your power curve, vortex generators and stuff like that. And then we have this project coming up with NDT scanning. So hopefully we'll be able to provide that for you in the nearby future as well. So definitely the focus for us here is to have a platform to do blade maintenance. It's not just a leading edge repair robot. It's a blade maintenance robot that we are providing here. So let me sum it up. We have a robot platform. It's very fast and easy to mobilize it. We have consistently high quality with the robots. We are able to increase the weather window where you can actually apply leading edge repairs or do other kind of maintenance tasks on your wind turbine blades. We are significantly reducing the health and safety risks when we are working with blade maintenance. And last but not least, we have something where we can customize solutions. So if you have a specific problem, we're happy to hear about it. And if there's a scale to the problem, it makes sense to automate it, then we can make a tool for the robot and solve the task for you. So that was pretty much my small presentation here of the solution we have from Robotics. Hope you like it, and hope to hear from all of you guys in the future. So I'll leave it back to you, Chris, and let's get some questions from the audience.
Absolutely. Seems like quite a few have come in here. Just want to point out, I heard you say the word eliminate twice, so that's excellent. Score.
Thank you very much.
That's what we want to see. Yeah, and I also saw some triangles in there, so all the safety guys around the world will love the triangles. But yeah, so we are getting 21 minutes left, so let's get into some questions. So we've got so scroll up through here. We'll try and send some out to everybody, but we'll give Christian an easy one first. Is the bump a backwards facing bump?
What is the question about the backward facing step?
Yes, so it is backward facing.
If you can say the backward facing step is in general bad for the aerodynamics, and what we can see from the computations and also from wind tunnel test is that the more towards the leading edge, we find the backward facing step, the more bad this is for the aerodynamics. So we want the backward facing step towards the trailing edge. And if we can actually also kind of make, kind of fade it out with some kind of a slope from the edge and towards the original surface, then it's also very good for the aerodynamics. I don't know if this answers the question.
I certainly hope so. So were we noticing more loss with lower wind speeds? Is that correct as well?
Again, sorry, I didn't get it.
The question was if there was more loss noticed at lower wind speeds.
Yeah, it seems the thing is that the power curve, it has, you can say the power curve starts at low power and then it gets up to rated power, and then it is constant at rated power. And the more of the energy that, or the more of the wind speeds that is in the part of the power curve that is where you have the rated wind speed and where you have constant power, then you are out of the sensitivity of leading edge roughness. So the bigger part of the power curve that is in the lower wind speeds and the bigger part of the energy that is in the lower wind speeds, the more you lose in AP. So if you are in a low speed site, then there will in general be more losses if it is a high speed site.
Okay, excellent. Karsten, we'll move on to you possibly. So quite a few sort of in the same vein here. So, just trying to decide, when to act, right? I mean, how do we know that the cost of repair will be worth it, those types of things? What sort of variables are required to use the tool there? So a couple questions sort of thrown all in together into one.
Oh, okay. Well, I mean, so you for the turbine itself, you just need the basic information: size, rated power, wind speed. So you can change the wind speed to the wind regime you're in. Air density, some sites is important. So those just are the basic information. For the erosion itself, you need the rain rate. So average annual rain rate, or you can plug in actual rain rates if you're really keen on getting a lot of details. But we also got to remember all the variations that we don't know. So for example, the variation from blade to blade, that's because of other things that we just, outside something you can get information about. So we got to remember that too. And then on the AP products, I made it quite generic. So, they can be refined to a specific product if necessary. But all in all, that adds up to, computed losses in the present and the future. You can move it forward, right? And you can add a dollar amount to that AP. And then you can compare that to budgets for repairs of different types of damages and adding AP if you like as well. So you can play out scenarios quite detailed with that set of information.
You possibly answered this one within there anyway, but I believe there was a question referring to, do we look at the local rain and dust conditions, or is there just a generality? Can you be that specific?
Correct. It would be preferable you should use the actual rain rate at the actual site. One needs to be aware some sites can have quite significant differences from one end to the other, if it's a large wind farm. So there can be some things that you sort of need to pay attention to in that aspect. It's typical where it's quite extreme weather, but dust, I have not specifically entered anything in on dust. It could be modified to include dust, but to get the dust information is not particularly easy, and it may be a very local phenomenon for very local places, so it's not a very general kind of problem.
So rain is significantly more of an impact then?
Rain, and it's consistent, right? Yep. So that's the other thing about it. But dust is sort of like maybe seasonal for a certain place. It need a very dry area, something like that. So it's a very regional phenomenon when it comes down to dust.
Yep, fair enough. Martin, we'll move on to a couple questions for you as well there. So one, how do you shape the leading edge filler contour? Is it, can you do any type of blade at all, or is it generic, or how does that work? Or is it to vary along the length of the blade and in what location it's at?
Yeah, thank you very much. We have designed a special squeegee tool that is able to adapt to various forms of various shapes of the blade. So we have actually one tool that can start from almost from the tip. We have a specific tool for the very tip of the blade, but then the rest of it is one tool that can adaptively adapt to the shape of the blade. So that's pretty much how it is. I think you can see it on some of the video material. We have also this squeegee blade that closes around the blade and then simply just follows the blade all the way up, and then there's like a spring mechanism that makes sure it adapts to the shape of the blade. So that's how we do this.
Okay, excellent. So I guess I'll lump a few questions together here. So what sort of weather window are we looking at? When can we not operate? What other type of inspections ahead of time would be required? And then I think, as far as the attachment, we see it's anchored from the top, but then what keeps it in a specific location on the blade? The rope will allow it to go up and down, but how do you go sideways? How does it stick to the blade, essentially?
Yeah. Maybe let's start with the last part about how do we anchor to the blade. So it's full correct. We have ropes. We have two ropes to anchor to the nacelle. So there's a dual system there for safety. Then we have a vacuum system. So it's attached to the blade with basically with a vacuum, some vacuum system below the robot. So it's stable while we're working. And then there's basically, when you change the angle of the robot and you're sliding up and down, then you will basically move it from side to side on the blade. So that's the basic principles of how we navigate on the blade itself. When it comes to the operational window, as I mentioned, it's the materials we're applying, the LLP materials we're applying, is very much setting the limits of when we can work. I mentioned temperatures from around 0 degrees up till 45-ish degrees is where we can work with the materials we're using with the robots at the moment. And humidities, there we're talking 85% relative humidities as I remember. And I think then there's often a lot of talk about wind speeds, and I think here it's important to mention that the robot can actually sit at the very tip of the blade and work up till wind speeds around 12, maybe even higher in 12 meters per second, maybe even higher. So we're quite wide operational window. We are also working on additional solutions where we will basically build a climate chamber around our tools, so we can also work in even more extreme temperatures and humidities, but that will be an add-on that we will deploy later on.
Okay. Is there any sort of preparation that needs to be done prior to the application of the filler? And then also, similar to that same question, can you do more than just leading edge projection? Can you do, lightning strike repair as well, that type of thing?
So the preparation we need, the robot basically does by itself. Of course, it's always nice to get a report from the blade before we start the work, so we kind of have an idea about where we are. But as long as we're talking surface repairs where we don't need any structural repair of the blade, the robot can do it all. And normally I would recommend, even though you have a part of the blade where structural repair is recommended, then typically we could just make the robot do the repair as a simple repair with cleaning it down, sanding all the eroded material away, and then applying filler and LLP material. And in this way you have basically repaired the blade, and then we can always, based on the documentation from the robot, we can afterwards assess whether we should go up afterwards and do structural repair in that specific area. So that is typically how we recommend to do it. But of course, if you want to do the structural repair up front, it's all good by me.
Have you tested different kind of roughnesses, example ZZ tape or discrete elements, to see if noise trend is consistent? And you may not have your microphone or camera on, Christian, if you're there. There we are. We can see you, but can't hear you.
Please repeat the question.
There you are. Refers to the noise. Have you tested different roughnesses to see if the noise trend is consistent? There's reference here to a ZZ tape. Not sure what that is. Hopefully you do.
Yeah, it's a good question, and we have actually tested this, and we have to analyze this carefully. What's happening for the airfoil, but this is to come to see how the noise from zigzag tape and other types of roughness simulators will perform. But you can say the logic here is that the boundary layer height will increase, and thicker boundary layers towards the trailing edge is actually good for the noise. So that can be some of the explanations here, that you have more also turbulence in the boundary layer. But we haven't these results yet, and we have to wait, and we will publish something in not a too distant future about this, because it's brand new, these tests.
Karsten, I guess we've got another one here for you as well. So should you always apply leading edge protection when you repair the leading edge?
Yes and no. It depends on your objectives, right? So if you're in a low rain rate, and let's say you lasted 12 years and you got to category 3, maybe you just want to repair and upgrade again, and like you might have to get back to it again 12 years later. So I think the choice of LAP should target your objectives. Like I said earlier, some APs do give a performance penalty that, the product may last forever, but it does have a small performance penalty. So sort of restoring to 100%, degrading below that number of that average of that AP for the product, that, there's a balance between the optimal and when do you want to go back and repair again. So that's why one of the reasons I made the tool, right? You can actually quantify this and say, okay, I'd probably rather, go back and repair it again. Like, like the robotics, it's a, a repair option where you get back to something that looks like the original. And so you get back to 100%, it tapers off, right, at some rate. And so that's a balance, and that's what the tool can be used for, to quantify that. And again, if the rain rate is really, really high, you might want to take the penalty off the AP product because it's going to deteriorate real fast.
Excellent. So what I hear you saying is you use leading and lagging indicators both. Wonderful. You're set up for success from a safety perspective.
Exactly the reason.
So, Chris, just to jump in, so I see there's a lot of questions here, and we will continue to answer those questions in the next 5 minutes. So, and those who don't get their question answered, we have them captured here in the background. So we will come back with personal answers to those questions. That was something about contacts and different stuff. So we will come back to those we don't can manage here within that time frame. Just FYI.
Excellent.
Okay, Chris, back to you.
So Martin, we have another one for you, and I can definitely see where this would come up. Are your techs qualified to install rotor locks, or do you require site support?
So yes, we have our own technicians, and they are all qualified to climb the turbines and apply the rotor locks and everything. But also beyond that, we are setting up collaboration with service companies. So we would actually like to have collaborations with all of you guys out there and start working with the robots. So it's yes and no, I can say, or yes, and we would like to collaborate with you.
Excellent. Okay. And then I've got two that I'm going to combine into one here. So is the application of leading edge protection limited to coatings, or can the robot also apply tapes? And in that same vein, can you choose, or can the customer choose, what specific product they want put on, or do you have sort of a limited inventory of what you can use?
So far we're only working with wet LEP solutions. I can't say that in the future we will not be able to do other LEP solutions, but it really depends on the market and what is the demand for the robot in the future. When it comes to more complex repairs, this is not the target for the robot at the moment. But then again, as I mentioned earlier, we have a target to have this robot being a kind of a Swiss knife that can fix any problem on your blade in the future. So it's a matter of getting all the tools, various tools for the robot, then we can basically fix any problem up there.
Absolutely, wonderful. Christian, we'll come back to you, I guess. So I guess the wind tunnel looks wonderful. I'm not sure I can fit a full-size blade in there. So how do we detect AEP losses on a real wind turbine?
Yeah, we have in the wind turbine industry, we have inherited the methods that were used for the airplanes. So we are testing sections because you are completely right that blades today are maybe 50 plus meters long, and they cannot go into any wind tunnel in the world. And for it to make it correctly, it should actually also rotate, and that would make it even worse because then it had to be 100 meter large or height of the wind tunnel at least, and we cannot do this. So we are testing sections, and then we are with our computational tools, we can then add the information from each section of the blade into these computational tools. So the information from the wind tunnels will be used in rotor prediction tools to find out how the rotors will actually perform. So this is how we do this to find out how the airfoils section-wise influence the aerodynamics on the rotor. So we do not have enough information about roughness on rotors, and it is also very difficult to measure on rotors because of the fluctuating wind and the uncertainty in the direction, and there's a lot of parameters flying around when you have a rotor running. So it's much more controlled if we can measure in a wind tunnel and then compute the rotor performance from there.
Okay, thank you. Karsten, got another one for you here. Now, you'd mentioned during the last question that there was sometimes a penalty associated with the leading edge protection. So, how much is too much? Is there such thing as too much leading edge protection? How do you find that balance?
So yeah, I mean, first order estimate, like why protect more than that was damaged, right? So I mean, sort of like, maybe common sense rather than, the other common sense would be more is better. Like, here in Texas, more is more and more is better, but it actually isn't true when it comes to leading edge protection, right? So I think, essentially as little as possible if it's an intrusive method. Right? If it's not intrusive, then of course you can do further, and also going back to like restoring the leading edge. If you're restoring at what is the future repair method if you're going to go back and repair it again later, 10 years later, or whatever the number may be, right? So there are this, again, I really can't give you the one-liner answer because there really isn't one. It's really up to the actual evaluation on that specific site and that specific turbine.
Okay, fair enough. We're getting pretty close to time. I do want to squeeze this last one in, though. I think this is pretty for all the marbles. So, Martin, this one is to you. When are you going to have the robot available in North America?
So the plan is actually to have it available in North America this summer. So we're right now working on getting all the robots ready, and we will start shipping systems to Canada and North America here in the beginning of 2021. So yeah, we're ready.
Excellent. And does it come with its own mask, or does somebody have to put one on for it to stay 6 feet away from people?
I don't think there's regulations on robots so far. I think we're
Perfect.
actually allowed to have robots working without face masks so far.
Wonderful.
But maybe the operator need one.
Yeah. All right. We're
Alrighty.
pretty close to our time there. So Lars, I'll turn it back over to you.
Okay. Thank you, Chris. Really appreciate your effort as a moderator, and there's thumbs up and high five for everybody. It's we have about 50 people left. It's very normal that an hour and a half. That's kind of what people can last on a call. So that's perfect. There are some questions we haven't been answering yet. We will do as much as we can, and feel free to email us or whatever. We're there for you anytime. Okay. Thank you so much for attending, and we will end the session now. Thank you.